Hello, everyone. My name is Professor Chris Mercer. I'm here to give a brief presentation on cosmic inflation theory, which is natural antecedents the idea of the multi-universe, right? And this is one that sort of, hits us, I think, with popular culture delving into this these days. In movies exhibiting the idea of alternate worlds and realities where, copies of ourselves or similar copies may exist. And I'm certainly, part of the vanguard of people which enjoy these things. And I remember the first sort of exposure I had to it was an episode of Star Trek. I believe it was 1969, where the Enterprise ended up in an alternate universe, and there's alternate Spocks and Captain Kirk's. And I thought, oh my goodness, I wonder what the alternate me would look like. And of course, as time went by, ideas like that began to, people thought that they were really silliest and supercilious at least, and very, very science fictiony and delusional. Well, they have become much more of a certain reality now. And in fact, the ideas that Gene Roddenberry talked about, way back in 1960s, it actually hit something that is more than just fiction. We're talking about fact. So my job here today is sort of present these ideas to you conceptually without hitting the rigorous details, the mathematics which are involved in this. Many of those mathematical details I myself do not understand. I am a professor of anthropology, but I'm fairly well versed in cosmology. It's been something I've dealt with, for maybe, or at least chimed in on the last 35 years as a more advanced amateur. So I'm here to sort of relay some information and tell you a little bit what's possible and what is not possible, at least at this point in time. Okay, so let's proceed. And first, I want to talk a little about the history, the relevant history of the attempt to sort of, get a good theoretical underpinning that will allow, multi-universe thinking. And the first path that was being made to this was by a cosmologist by the name of Alan Guth. And he began his work in the late 70s, and by 1980s, he was putting out some really bona fide theories and what we call cosmic inflation. And I'll explain cosmic inflation as we move through, but right now, just trying to take it in a little bit by osmosis. So what he was attempting to do is solve some problems, some irregularities in the sort of cosmological equations which Albert Einstein had produced, his relativity and special relativity, formulas, in which he conceptualized, a universe which was the product of a Big Bang, but a Big Bang in which operated under the normal physics in which caused everything to happen in the world today. And his particular special relativity equations, predicted, if you follow them very closely, a universe which is not exactly what we see, which is visible. It's missing some of the key elements that we would have expected if we had had a normal, expansion period since, quote, the Big Bang. And he was looking for, ideas about how the early universe, when it expanded, would have produced, some pretty heavy gravity waves, which would have dilated or distorted times in many ways, creating large curvatures in time. Instead, what we find is, for the last 13.83 billion years in which our universe has been here, is a relatively flat space, space in which has expanded, right? But it continued on at a relatively linear march, where time dilation, which we see from one area to the other, is not significant whatsoever. In other words, a uniformly flat universe. The only way to explain this from Guth's perspective is that the initial creation of the universe, happened utilizing laws of physics which do not operate in this world. They're in a different world. And the initial expansion allowed for the primary movement of the universe to sort of surpass gravitational wave formation. Whereas there was a set of dimensions which were operating during the expansion, which sort of skipped a lot of the things which would have caused what we would see visible, normally an Einsteinian sort of view. So he began to construct, a very elegant system of mathematics to sort of, describe what this would have had to have been like. And then Guth went on to start looking for evidence for this. One thing we think about mathematics is that there are no mathematical hypotheses, there are postulates. And math is designed to model what we see in reality. And when you get to a very high level of mathematics, in other words, you're starting to predict a model. Now he's got to go search for the actual pattern of real evidence to fit the model. So the race was on. And let's see what we found. Okay. Well, sort of next in line, here I said the evidence, but we sort of sift through some of this stuff, is that two sort of sources of evidence came in, and one a little controversial and one particularly more solid. The more recent one is the one that's a little more controversial. Back in 2014, the Bicep 2 project, which is Bicep 2 is just an array of telescopes which sit at the South Pole. And it's a large array of telescopes which are actually sifting the universe very deep in time. They're going out 13.8 billion years looking at light that existed at the very early formation of the universe. And looking at the way that gravitational forces would have polarized or bend that light, right? Sort of the shifts in the way it would actually appear to us, in the visible sort of spectrum of light and also the invisible spectrums. What Einstein said would have happened. And what we're seeing is something very different in the early parts of the universe, according to those gravitational waves, the way that we see the light being perturbed, right? So this started to support, Goose sort of thinking about this stuff. But other scientists sort of chimed in and say, you know what? When you're looking at out in space, you're also looking through giant structures of gas and dust, which can give you that same sort of effect too. And you're at such a distance, do you know if you're looking at reflections of gas and dust or straight within the light within itself? Because that could make a substantial difference in your interpretation of something that's causing gravity waves at that point, that far back, or no gravity waves at all. And we need to be very, solid about this. We need to know one definitive way or the other. Well, that has been left up in the air. Now it's sort of like people who chime in that want the Bicep 2 people to be right, and those that hate the inflationary sort of model, the old sort of school that want it to be wrong. There's a lot of politics have been engendered with that, which we can see with the conservative sort of illiberal debates are happening in the world right now. Well, the next piece of evidence, which is called the cosmic microwave background, the CMB, really is looking at light. That's not the oldest, not the oldest sort of forms of gravitational waves, but actually the oldest forms of visible light. And this visible light's there at about 400,000 years. Light doesn't become available in the universe. But looking at the pattern of this light, and what does the light can actually tell us about the formation of the early universe? I'm not going to go into that. And I'm going to leave it to a separate slide because it should be part of the flow of it. But that's the one that I have a little check mark to. That's the real pay dirt here. And what we know so far, with the images I'm going to show you, that no other theory other than the ones in which drop from Guth, the idea of an inflationary model of the universe, which I'm going to unfold to you, can explain that image. And after that inflationary model explains that image, there's only one way to go from there. It leads us directly into thinking that multi-universe is not only just a possibility, there's a high probability that we are living, in realities which are dominated by multi-universes outside at least our sphere. And we'll talk about the number of those and the probabilities of getting a parallel universe, the stuff that the magic is made of in public imagination too. Right. So, inflation, as I say, it really does imply multi-universe structure. I don't have the time or the efforts, or I don't think I have the ability to follow the mathematics which are involved. But two of the best physicists in the world, again, Alan Guth, and one is Andre Linde, probably one of the most respected astrophysicists in the world, have said this, and they're almost chiming in parallel about, sorry for the little pun there, parallel about parallel universes, right? So Alan Guth says this, and I'll read these quotes: it's hard to build models of inflation that don't lead to, right, a multiverse. He says it's not impossible. So I think there's certainly research that needs to be done. But most models of inflation do lead to a multiverse, and evidence for inflation will be pushing us in that direction of taking an idea of a multi-universe seriously. Certainly. And that's a statement which he made back in 1982. In 2008, Andre Linde makes this statement: it's possible to invent models of inflation that do not allow a multiverse, but it's difficult. Every experiment that brings better credence to inflationary theory brings us closer to hints that the multi-universe is real. And certainly that's really why we've been building the large, the super colliders, such as the Hadron Collider. That we're taking particles, and smashing them together and driving them into energy levels in which they will literally move out of spaces of time, right, back into the inflationary corridors and re-enter areas in which our visible field, where we're tracking them, which would follow the mathematical and theoretical sort of models of inflation as well as multi-universe theory. So without going into that too critically, the trillions of dollars which are being spent on these super colliders is well worth it as far as physics is concerned, because it's beginning to confirm this idea of inflation and multi-universe direction. So the next guy who comes in, which is a little more recent, this guy hits in about the 2000s and made a big splash because he starts thinking about this idea that these guys are looking at the physics in which govern, inflation, the first moments of the universe, right? And looking at, how we can describe a new sets of physics for the structures that existed then. A guy by the name of Brian Greene, of course, at Cornell too. Cornell is a hot spot at this point. So we need something more grand and unified. How do we, layer physicists? The classic Newtonian physics, the Einsteinian physics, which state relativity and special relativity, as well as the new stuff that's been hidden by Guth, right? How do we take Guth's ideas of string theories and add them together into a grand unified theory? And once we produce a grand unified theory, what sort of structures are possible within a universe? What do we know about its structure? All universes and the nature of space and time itself. Well, through a very elegant system of mathematics and experimentations, which drops out of these supercolliders, he finds that there's 11 different space-time dimensions, 11, right? And 7 of these dimensions are above time, right? And these, to exist, need to be compacted into very small scales and distances, very small. And that is what we call the singularity. The idea of when you go to these movies, when you see the black hole, things are so cramped and small and pushed together, the dimensionality begins to decrease down. So we're talking about a singularity. But singularities which are even greater than the densities of black holes, right? We're talking about primary energy, right? Are compacted up into 11 different dimensions, okay? And what that does is allows us to understand that sometimes energy gets packed so much the dimensions begin to be moved in together into a single dimension, 11 dimension, to where the lower dimensions don't have a life of their own anymore. And that also means time, which is considerably a lower dimension. It's only a 4th order dimension right above the 3 in which we live in. And of course, time, which is part of our lives too. And the high levels of singularity under compression, where gravity, right, is no longer, it becomes extreme, time begins to disappear, as well as 3-dimensional structures. These are places in which are out of time. And that's where our new physics are describing too. Things that not just happening during the Big Bang, but happen before the Big Bang, in the real otherworldly places. So M is not for madness, right? M is for a brand new way of looking at reality, which has both experimental backing and mathematical credence because it's elegant and it's actually perfect. And it works out well as a grand unified theory. Okay. So when we talk about it, get more practical ideas about everything. How big is everything? Well, when I think about the Earth, I think it's pretty darn big. And I think about our sun, gigantic sun that we have is pretty big. But all these things are impecunious. In fact, even the size of our universe is very, very small when you're thinking in terms of multi-universe, when you're thinking in terms of infinity, they are. Now, I'm going to present some numbers which hopefully will allow you to think that we're living in a little more humble structure than we suppose it is. Even though our universe is 92 billion light years in diameter, so how wide it is. And when we think about, light years, we hear, all these science fiction sort of programs. Well, what is a light year? Let's talk about a light second first. So light can go around the Earth 7 times in 1 second. That's 1 second. So think about how far that light can go in 1 year, right? Now think about how far that light can go in 92 billion years. That's how far our universe is across. And what's interesting is 13.85 billion years ago, it all started in a package that was roughly around 17 millimeters or 17 centimeters across, about this big, about the size of a basketball. So even though it has grown from that state to 92 billion light years across, I still think about it as a relatively small structure, right? Because I'm thinking on infinite time and infinite size, which is really where our head should be at now. Now, what about our universe? What's it contain? What really is it? Well, it contains a fixed amount of something, a fixed amount of matter. See, one of the results of the Big Bang was the appearance of matter. Before it happened, matter did not exist because this is a 3rd-dimensional structure, right? Matter is part of that. It used to exist in a higher level dimension where the particles in which we see did not exist. They were in different structures. But right now, as a result of that, we have 10 to the 90th particles, which is a relatively large number. And I'll agree that's probably the largest number you've ever encountered until you see the rest of what I have to offer you here. 10 to 90 particles, right? So that's a lot. And let's consider that we're living in an average size universe. An average size. Let's say the average size has 10 to the 90 particles. They're all clumped together, mostly under their own gravitational influence, real particles. Some of them independent stars and small star clusters. Some are concentrated together in the gravity in large galaxies. And some galaxies are attracted together and create, galactic clusters, even lanes of twisty lanes of galactic clusters, which we can see, in really large ray telescopes. And thus, that's where all of our matter is at, right? Each one of these galaxies, filled around 1 trillion stars and roughly 0.5 trillion galaxies, right? And what I consider a very small universe. Yeah. Okay. Now, despite its size, like I said, it's really quite small because of the infinite distances, right? And what we also think too about their place, why it's small, is a universe is a structure that's bounded in time. And it has a very limited space in time. Okay, we do. We started at one point in time, and not before a point, not after a point, but one point in time. And we're traveling in that point of time. And we're traveling at the relative rate of motion of particles. We're going to think about what time is. Time is motion. Now think about it. If everything around you stopped, I mean, not just froze like this, but stopped. All the particles stopped. No motion, nothing. Time essentially stops. If that actually happened, your particles couldn't stop, you go right back into a singularity. You would collapse into a higher order dimension because time would no longer exist. Time is motion. Time is change. Okay. And the thing about it is, it happens at a level in which is instantaneous. Because as soon as you begin to move from one position of particle to the next, you leave time behind. And there's nothing behind it because there's nothing in the past. For humans, the only thing in the past is your memory, but the past does not exist. It is empty space. And before you get to the future, what you have is empty space and time. That slot is free. Well, here's what we know about the modern laws of physics that are specified in M theory, that empty space is not allowed, right? Both in time and actual volume is space. Even the space we see around us, which we think is so empty, is not. There's lots of stuff there. And that space is full of fabric, which is constantly expanding around us too. There's always activity in it. And so is it with time. Digitized time in front of us and digitized time in back of us. There are things which are happening within it as we travel through it. That's our first clue, thinking about where the other universes just might be, okay? So a very limited space at that. So a little nutshell model here. We'll get to something more, I think, sophisticated soon. So in the very beginning, of the universe, the thing called this Big Bang happens, right? And the Big Bang is a little different. We think it's sort of two things that are going on, actually three things that are going on. We have a singularity state, which is bound up in, probably 11 dimensions. Everything's probably in 11-dimensional structure at that point. It's 11-dimensional structure. Okay, that's it. Okay, because the energy levels are so high. The other dimensions are collapsed below it. Possibly we have, dimensions, maybe 6 through, 11 functioning in this area here, okay? Well, what happens is at some point that energy reaches a transformation point, which we'll look at how that happens soon. And as it transforms to a lower level, right, it ends up during what we call inflationary energy. So inflationary energy takes over. It's not yet within the space-time that we think about. It hasn't gotten into the fourth and third dimensions, the first, second dimensions yet. It's still racing down the 11th towards the fifth dimension. And as it's moving through this dimension, space, the fabric of space begins to inflate. It's an inflationary period which we have. And it only happens for fractions of the second, so small, like 10 to the negative 30th of a second is all this inflationary period happens for, but it's so critically important because that's exactly what guys like Guth were trying to understand. What was happening in the laws of physics within that inflationary state that allows us to see sort of different dimensions as they unfold. And of course, what's going to flow from that is the possibility of where these multi-universes exist and how they were actually constructed too. Now, after that fraction of a second time, the normal laws of the universe take over, the Einsteinian things which we see and the Newtonian things we see, and space still continues to expand, but at a much more normal rate, a much slower rate. A rate in which we see. Now, in the inflationary period, which we'll talk in a little bit about the speeds, they're rapidly fast. I mean, faster than the limits of normal physics will allow it to actually happen, which is why we know that the normal physics which we have in this world can't be governed. We need a new descriptor for that. And that's what Guth was actually doing as colleagues. So this universe goes through a period of transformation and where there's not even light available. Particles beginning to form, but the particles are glued onto even photons, the stuff that actually creates light. There's no free light flowing anywhere. The universe is dark. It's hot, plasma and dark. The photons themselves don't even become free to be illuminated and radiate out, right? Until about 380,000 to 400,000 years ago. And that's when we get this first scattering of light, the first glow. And our telescopes can see that. This is our cosmic microwave background. So we can go in, we can look at that. We can take our telescopes and go way across the universe, out to 13.85 million years ago. And we're seeing the first light, the afterglow of that. And that gives us some incredible evidence to what that inflationary period was actually about. And we'll be looking at that soon. Well, after the first light begins to happen, gravitational forces begin to interact with matter, the first stars. And then by about 1 billion years ago, the first galaxies and superclusters begin to form until we reach the modern universe in which we live in today. Okay. So prior to the Bang Bang, wow, what was this world like? A whole different world. Now, we've used a lot of data from supercolliders, to sort of look at what's happening, this, and see if the particles in which we're moving and colliding together, are they behaving? Are they moving into different dimensions? And are they moving back into ours? They're flying back into normal time when we expect it to. And in the transformations, the same as what we actually predicted. As for our models, which govern inflationary space, and actually, they do. So we're extremely happy about the experimental evidence, which I don't have the time to actually present to you in rigorous detail. But what we can say is that when we talk about this inflationary period in the very first part of the universe, we have to sort of shift our perspective. We think about a different sort of dimensionality and a different sort of way in which physics would operate. We talk about inflationary energy. We're not talking about something that has a center. Right? We're talking about inflation that happens at all points at once in all places. And we're not talking about something that has heat per se. That's the product of a three-dimensional world. We're talking about rapid, dense inflation without heat. And until that inflationary period is over and the transformation of Earth, then we're going to get what we call this violent transformation to the particles which we see and the rupture of heat release in which we have. So here we're operating on a different sort of form of physics. And a hyperdense state, which is heated but unfeelable, right? And prevents the formation of matter. In the inflationary period, we don't have 3 dimensions, okay? Neither do we have the 11 dimension. We're in sort of an in-between dimensional formation, right? And the thing about it, it's fluctuating, between the space around us and a wave-like function. It's a constant fluctuation. It's in this dimensional fluctuation and flux. And it's the highly unstable period in which we're beginning to get to the period in which we're going to go through normal expansion, okay? All right, so let's explore this a little more detail. If we can go before this idea of this inflationary energy, what existed before and how was it actually produced? Okay, all right. So in that other world, before inflation exists, in that 11th dimensional area, we have a singularity, right? And we've talked about singularities. You probably heard them a lot in science fiction or maybe even physics courses. But to describe a singularity, when you talk about what we're talking about, singularity just means an existence in a higher dimension where the energy levels are so high to allow that formation. Okay? And from what we can understand by this 11 dimensional, probably down to fifth or sixth dimensional sort of space, 2, 5th to 6, 11 together, it's like a sheet of fabric, moving and rippling. It's a rippling form of energy, we will see. Okay? Rippling form of energy, vibrating up and down, rippling up and down. And the thing about it is that rippling effect keeps the universes locked together between 5th and 11th dimension, right? It keeps everything in a harmonic way. It's a harmonic system which we're seeing, right? But like other waves, which you see in the sea, ever seen the rogue wave come in that begins to double up on one wave, right? And the waves begin to overtake each other, driving troughs sometimes very deep, right? The low parts of the waves, the energy levels can go very high, and the high parts can go very high too, keeping in the higher dimensions, but maybe pushing them down a little bit too low below trough energy. And if you run below a trough energy that keeps the higher level orders together, you start forming lower level orders and a runaway sort of formation until you get the eruption of lower level, dimensions, and that begins space inflation. And that period of energy literally buds off in time, begins to form, begins at third dimension and separates itself from upper dimensions as time forms, mass occurs, and bam, you have a structure that begins to develop in time, right? And that's what we're seeing right now. And that little first formation you're seeing there is just about the size of a basketball in which it occurs. Okay, so this dimensional transformation, right? Man, it happens so fast in that initial formation, right? To get the basketball, to get the basketball stage, which that transformation happened within 10 to the negative 36 of a second. That's just so fast, right? The energy shock, but bam, it hits, right? And when it starts going through the inflationary phase, it is unbelievably fast. Okay. I'm talking about by the time that we're looking at 10 to the negative 32 seconds, from 10 to the negative 6, 10 to the negative 30, that's small. That volume of 17 centimeters had grown 10 to the 300th time, right? 10 to 300. You know how big a number that is? Like 53 light years or 83 light years within I mean, hundreds of zillions of tenths of zillions of seconds. It grew to that speed. That is billions of times faster than the speed of light. That far surpasses anything that's possible within the universe we're having today. Those sorts of inflationary speeds are only possible in the higher order dimensions, as stated by Guth and by Brian Greene within their elegant mathematical structures and by the stuff that we have from the Hadron Super Collider. Okay. Now, at about 10 to the negative 30 seconds, this is when the inflationary period sort of ends. And what happens is that we get a conversion of all the inflationary energy, reaches a certain low state, and it converts instantly into matter at about 10 to the negative 30 seconds. Boom. And by about that time, the visible universe, right? Well, you can't see because there's no light, but the matter in it begins to appear for the very first time. Shabam. Now, this inflationary period, of course, is driven by expansion at all points. And it would be like, you're taking like a balloon and drawing dots on the balloon and blowing it up. And watch the dots. They're not moving towards each other. They're moving away from each other. In fact, if you could put dots inside the volume space somehow and blow it up, you would see all the dots moving away. There's not one point which is exploding. It's everywhere which is moving away. That's what I mean by inflationary energy. There is no bang. There is no center, right? Thus, as this thing begins to get carried away and how huge it is, what happens is because it's not dealing in real time yet, where gravity is even present at this point, or it plays any sort of role whatsoever, no gravity waves are being generated by this activity. The types of things that Einstein said must be there to cause a dilated or warped sort of universe, a curved universe per se, in which we don't see because it's remarkably flat. And that's what really started this sort of investigation and why we know we are in a different dimensional sort of world. Okay. All right, so we can see this sort of expanding things happening here. But what happens is that while inflation energy does this up to about 10 to negative 32 seconds, it slows down right after that as matter is present. And when it begins to obey the normal laws of the universe, nothing goes faster than the speed of light. And we still continue expansion, but it's not inflation. It's the same type of motion, right? There's no center of explosion. It still contains this swelling from all areas, but it happens at a normative rate below the speed of light. And has continued that since 10 to the negative 32 a second till here we are 13.85 billion years later. And that accounts for the 92 billion light year diameter which we have. Now, if our universe had kept expanding the way that it did with inflationary energy, it's almost incalculable because it's exponentially increasing. If that would have kept going, the limits and volumes would have been just absolutely incredibly monstrous. It wouldn't be possible. It would be incredible. And that's why those unique physics are at play within the inflationary model. Okay. So something that's a little bit more refined. Let's look at a more refined chronology than that little baby one I gave you before. When we look at disinflation, we see the first comet back radiation, we see the first stars and finally galaxies. And what's happening and what are the time points here? So inflation, we have the original sort of fluctuations that happen with that 17 millimeter ball. Bam, we pop out of singularity. We're tumbling down the 11 dimensional. Also 11, then we got 10 dimensions, we got 9 dimensions, we got 8. Well, all these, we'll probably have 6 to 11 automatically there. So we start triggering the 5th dimension becomes present, right? The inflationary spatial energy in the 5th dimension takes over, right? gets below a certain point, and then bam, we get matter formation within about 10 to 36 seconds, and bam, particles form. Okay. And from that point, it's just particles cooling down enough to begin to join to create more complex molecules. And then the atoms, which we see, atoms come together to form biochemistry, become together more complex objects. And finally, we get recombination of all these things, and light begins to separate. And we see that background image about 380,000 years ago. And of course, we get normal progression of the universe. And we're not going to be looking at that point because our heartbeat is still right here. And those first 10 to the negative 32 seconds. That's really where the action is at, and where our story of the multi-universe is going to be centered. Okay. So inflation versus expansion. I've been through that. Inflation is hyper, it's super fast, dozens, millions of times the speed of light. Expansion is not, much less than the speed of light. Okay. But the thing about it is that we're in inflation to think about it, that everything is doubling at about every 10 to the negative 35 seconds, right? So they think about how actually fast that is, the sort of laws of physics that must be governing that. So I want you to keep that in mind too, right? I also want you to think about this too, that once our universe is present and particles are there, like I mentioned before, now we have a universe of matter and a universe that is governed by time, okay? And when negative 10 to 32 seconds occurs, that establishes the beginning of time. Before negative 10 to 32 seconds, there is no time. It doesn't exist. That dimension has not been unfolded yet because particles are not there to constitute movement and time whatsoever. It's a place outside of that sphere, okay? Now, something else about inflation here, I think I should put a push in here. That as inflation continues, inflationary periods stop at some areas for other areas. So when we see inflationary space begin to move, some areas drop below the certain energy lines and convert to matter, right? The stuff which we see time begins and matter begins, and some areas continue to inflate, and then they peter out, and then they become part of time with matter. And then some areas continue to inflate, and the inflationary areas push other areas away, and which become matter, right? So inflationary space is keeping new periods of time and matter. And those new periods of time and matter, which are happening as inflationary energy is petering and expanding, are universes. Our universes, every time one area of the inflationary energy begins to slow down, losing its vital forces, unfolds its third and fourth dimension, time occurs, but bam, a universe erupts, okay? Because the rest of the inflation is not in time. It's existing out of time. And then as it peters out, another universe unfolds, but bam, another universe. And as it goes on, another universe unfolds. This is really the source of multi-universes. And that's what we predicted right from the very beginning, exactly what Brian Greene was looking at all the way back to Gunther. This is the stuff that must be happening, simply because the volume of that inflationary space in which we know is monumental compared to the number of particles in which we have within our own universe, right? This is what the prediction is where was the extra energy? As much as 17 centimeters doesn't seem like a lot, it is massive when we're talking about the type of dimensions that these things are folding up to. It's finite within itself, but there is leftover for countless universes to actually form. And the physics behind inflationary space, the mathematics predict the slowing of space in which will be uneven, okay? All right. So that cosmic background radiation image, what does it tell us about it? I mean, why is this so important? Why is this light capture? You know, it's roughly 380,000 to 400,000 years old when light becomes firstly visible. Well, here's what you think about. This is a capture really of not just microwave energy, but temperature. Relative, frequencies tell us what the temperature was at in the universe. And this is sort of a 360-degree bubble. What's all around us, right? Which is roughly around 380 to 400 million light years across at this time, right? It's all around us. And what we see are these colors out here. So let's look at the deeper blues, let's look at the greens and the yellows and the reds. And you would think that, oh, the reds are the hot spots. Well, they are, but how hot? The difference in temperature between everything, between the darkest regions, the coldest regions, and the hottest regions is only 0.0002 degrees Celsius. Everywhere we look, that's the maximum difference in temperature. Over 400 million or 400,000 light years, 400,000 light years, that's it. It's a remarkably uniform, cool picture, right? I mean, well, like a uniform glow. It's warm, but it's glow everywhere. It says everything must be inflating. There is no center. Explosions don't leave temperature traces like this. This is not the way the radiation from an explosion would happen. This tells us inflation began this way because no other theory, no other formula, nothing can explain this except inflationary theory, goose theory. The only thing that can at this point, for 41 years now, no one has caught up with anything else that can explain it except for that one. So this image is actually wonderful, which is why I love science. I love science so much. So the wonderful things, if you learn how to interpret things, what these things mean, is what it could tell us about our universe and our existence right there in a nutshell. Okay, they're fine points. Again, inflation is not like it's not like a ball either. So when we think about the inflationary period, we have to be very careful about this idea of a ball expanding. That's within our head because we live in 3 dimensions, right? We got to see things in 3-dimensional space. Now, this thing is roughly 17 centimeters. 17 centimeters of what? It's more like a quantum fluctuation that spreads out like a field, right? A circular field, right? All wrapped up, not within its corners of time, but around each other, a circular field of quantum energy, okay? So it's not in a 3-dimensional space, it's wrapped up in a different sort of structure, okay? Now, as it begins to inflate, the quantum fields have their own troughs and valleys, right? When they go through the lower troughs and valleys, that means your energies drop below certain areas and enter 4th and 3rd dimensional fields, and they have their own sort of, drops and inflationary sort of moments. And those inflationary moments are really the expansion of the known universe, right? That's really the 3rd dimensional space, and time begins. So is that quantum wave of the expansion of this inflationary expansion going up and down? It goes below, bam, new universe, right? And it goes down, up and down, a lower universe. Another little trough that goes down is expanding, moving. The inflationary energy forms another universe. And this wave continues on and on and on and on and on and on. How far that wave continues, we'll talk about in a little bit. If it continued forever, of course, just one movement out of singularity, right? One wave of that inflationary energy could produce, an infinite number of universes. And some scientists actually thought that. I disagree with that, and I'll tell you why in a few moments, okay? All right, so let's go on. I think I've sort of hit some of the fine points now. All right, so we're talking about this inflationary energy again. But think about it this way, we're moving out of the quantum wave, each one of the blocks there together are really universes which form. And the areas themselves are sort of the inflationary energy driving, moving, and as soon as the area reaches a point at which it drops below a certain level, a known universe expands, but the other inflationary energy that's around it continues to move out. And it drops below a trough, producing other universes until the inflationary energy runs out of steam, right? And the last universes are formed. And we have bubbles, bubbles of universes. But the thing about it is that universes don't all start together. They're very close to each other, in time, because inflationary energy does this all very quickly within 10 to the negative 33 seconds or so. All of these universes are actually created. It doesn't happen over long periods of time, very short periods of time. But we talk about what is the future and what is the present. What really sets the future away from the past? Is it a 10th of a second, a billionth of a second, 100 zillionths of a second, or is it infinitesimally small, right? Which means other universes can be infinitesimally small ahead of us, in distance ahead of us in time, and behind us in time, because that's the way they're moving out of the inflationary energy model into their own 3-dimensional packages, one after one after one after one, interdigitized in time. Some beginning slightly ahead of the others, right? We might start, next universe starts, next universe starts, next universe, starting the clocks, right? One right behind the other. So it's not, where these universes are, it's when the universes are in space. That's really the interesting part of dealing with this sort of physics. So are there an infinite number, right? Are there an infinite number? Well, one sort of line of physics goes off to saying that this inflationary energy, if it keeps a continual feed, right? If this inflationary energy is dropping out of the singularity, a continuous feed, if it's doing that, it's just pushing continuously into lower dimensions, on and on and on and on. And there might be this continual leak. The energy is leaking all the way out, forming endless chains of universes constantly. Okay? This we're looking at, we don't think so. We think the singularity in the 11th dimension isn't having this constant leak. That, you know, the regular periods in which it drops below energy rank, when it's like a waves begin to get on top of each other, driving the troughs a little bit lower. We do believe it happens in regular, you know, intervals, constantly producing new inflationary moments that produce a finite number of universes every time this happens. Because it drops below the energy trough, creates inflationary energy, but then a series of universes will occur until the next singularity drops below the trough. Another inflationary period creates a number of universes, right? On and on and on and on. And we can't think it happens as one time because, you know, why should it? Physics doesn't happen that way. When things happen, they continually happen. Okay. All right. So universes we got to think about are not so much separated by space, but they're separated by time. Okay. Thus, there are an infinite number of universes ahead of you because there's an infinite number of time. You know? And there will be an infinite number of universes behind you because there will be an infinite amount of time. And this process appears to be ongoing and unbroken. At least we don't have any way of determining that it has been broken or not. Okay? We see physics happening as it's happening now, as universes are being formed. We can use basic principles, you know, that we apply every day called uniformitarianism. In geology would state that the principles in which we see forming the Earth and changing the Earth right now have happened in the past. That's what's created the world, and they're going to continue going on and shaping the world in the same sort of way. So we can apply this, and we can see that this is an eternal process. Now, in all of this eternal process, you know, this is our immortality guaranteed, you know, because we're gonna have all, you know, alternate universes, you know, multiple copies of you and me. I don't have to worry about it. I'll be immortal, you know. What are the odds of it? What are the odds of an exacting copy or parallel universes or universes? Well, you know, it seems to be a way we can actually calculate this now, you know. I mean, it's kind of down and dirty. There's not going to be exacting on it. But once you look at theology, you realize I don't need to be all that exacting. Let's have a look. Okay. All right. So what we think is when we get the movement out of the first singularity, okay, looking at normal inflation, not internal inflation, the energy of that 17 centimeter ball that drops out in first inflational energy goes in that, you know, all the way down from 11th to 5th dimension and finally, you know, expands rapidly, has enough energy as it creates universes one after the other as it drops out of the inflationary state to produce 10 to the 10 to the 50th universes, right? That's 10 to that number down there. That is probably like one of the biggest numbers that you have ever seen, right? And you might think that that's infinite. It's infinite. It's not, because there's still an infinite, but there's still a finite amount of that inflationary energy available, right? In those dimensions. And that's what we figured, that it can actually create that many universes every time this occurs. Okay, so that's a lot of universes. So the odds of maybe getting something like us is high. Look at that. Okay, and that's just as one event. Okay, that happens probably every 1 to 10 to the 33 seconds. Okay, so you can get 10 to the 32 inflationary events if this is happening constantly within, you know, the inflationary structure, the major structure. We're getting constant waves where we're getting new universes all the time, and one happens every 10 to 32 seconds. Bam, you're getting 10 to 32 times that number of universes every second. So we're talking about multi-universe. We're not talking about a few things around us. We're talking about infinites constantly pouring out of the system. And one of the problems that we have is when I say infinity, infinitely large, you guys don't seem to understand what infinitely large is. That means our universe is impecuniously small. That number you're looking at right there that happens every 130 seconds is an infinitely small number compared to infinity. Infinity means it don't stop ever. Okay, right? So I'm still doing what I call small thinking at this point, right? Now, in our small, impecuniously small universe, what's in it? Well, we know there are about 10 to the 90th pieces of matter in it, right? Small particles that produce everything. 10 to the 90th. That's still a huge number by our standards, right? And probably about that many in each universe. Let's give ourselves an average universe. Why not? You know, we're here. You know, you take a random person, you know, you're probably going to get like a male 9.5 inches tall. If I take a female, probably 5'5" on average. So, okay, say everything's average, 10 to 90 particles. Okay. Here's the deal. If you're going to have a parallel universe, any universe that ever existed, not just that many universes existed at one time when ours was done, that all of the histories of those particles or interactions have to be exactly the same, all 10 to the 90th particles. And not at just one point in time, but for all 13.8 billion years in which that universe has existed to arrive at a parallel universe, okay? Right? So how many interactions will you have to have, will be going on that have to be exactly the same, okay? How many different possible outcomes are there, per se, between all those things? Here's how many there are. We can use some statistics called factorials. Okay, a factorial is this. So let's say 5 factorial. 5 factorial is very simple. 1 times 2 times 3 times 4 times 5 is equal to some number. That's the factorial of 5. The factorial of 10 is 1 times 2 times 3 times 4 times 5 times 6 times 10. That's the number. That's the number. Well, the number of interactions of 10 to 90 particles is 10 to the 90 factorial. That's 10 to the 90. You take all those numbers leading up to 10 to the 90 and you keep multiplying together. That number, I cannot begin to write down. I think we've calculated it takes somewhere around 500 million years for me to write the exponent of that number. If I were to do it writing all for 500, I think it's 570 million years. I think I estimated how long it would be to do that. Man, do you know what are the odds of another universe having that same sort of interaction with that many possibilities? Okay, what are the odds? Okay, so we can even talk about, we always know how big a factorial is. Here's a factorial of just 1,000, not 10 to the 90. That's one number you're looking at. That's the factorial. Every number going up to 1,000 gives you a number that long, all the way across, all the way down. Now imagine that being billions and trillions of times longer than that, right? That's how many possible combinations that there are, right? It's just unbelievably small that we could get another universe that we parallel to our own. I mean, and even reasonably close to our own. Okay, but there may be a saving grace here. We'll have a look at this. Okay, but the thing about it is that look at how many number that are made per inflationary event. Okay, and that's made within roughly 10 to the negative 35 or 10 to the negative 32 seconds. And in the singularity, which you're looking at that picture, right? That waveform and that 11-dimensional space constantly moving, right? Rippling, right? And sometimes these ripples gang up and double on each other and force a lower trough again, right? If we can think about that happening, it may be half as slow. So at the time it takes one trough to go up, one down, I mean, one could help double and push it down lower. So it would happen in about 2 times 10 to the negative 35 seconds, okay? Which is still roughly the same thing as 10 to the negative 35 seconds. So if you invert that, that means every second you get 10 to the 35 new inflationary events, because that's how many things are dropping off below the energy plane here, producing 10 to the 10 to the 50 different universes every time it does that. Every second, 10 to 35 of those every second. So how many of those would it take till we could get some combination of the same thing, the same histories that would happen in our universe, right? How many? Well, let's do some math here and figure this one out. It's not so hard to do, okay? All right, here we go. So 10 to the 90th factorial, that's the number of unique interactions possible in the universe, okay? Divided by the number of universes produced in a second. Let's see what the odds are in 1 second, okay? So if you actually run that number, the odds are so small. The number is so small. It's too small. We call it large. The decimal points are too small, too large for any known computational device on planet Earth. Okay, not very good. Not very good. Even in a second, all those universes, right, that you're going to get. Okay, 10 to 10 to the 50th, every 10 to the negative 35 seconds, right? And then we got to invert that and go to 10 to the 35, and of course, multiply it by 2 to reduce it by half. Too small. Okay, how about this? What I've done for you here below, the number of unique interactions that have to happen in the universe, of all the possibilities, okay, divided by the number of universes that can produce per million years. I've taken all those seconds and multiplied them to get a million, to get a million-year pattern. That's the number on the bottom, okay? Still, when I take 10 to the 90th factorial, which is incredibly huge, by that huge number in the bottom, 10 to the 90th is so overwhelmingly large, it's still too large for computational devices, right? The odds are none. There's never going to happen, not within a million years, where you're ever going to get another multi-universe exactly like yours. There can't be another you within a million years. But here's the thing. Time is unlimited, it's infinite. The number of interactions in the universe is statistically finite because each universe is a finite space. That's the number of interactions that you're going to have. It's a known finite number. But the number of universes are continually being produced, therefore they're infinite. Thus, at some point in time, you will have a parallel universe generated. Okay? You will. There will be a parallel universe. It's a matter of not where, but a matter of when. Okay? That's right. Because there are a number of infinite universes and the difference between them is finite, there will be countless parallel universes and replicas of us. Okay? Now, but where those things are, where the twin is a matter of distance and time between them. There's the issue, the distance in between time. Now, and how those time periods between realities occur is going to be staggeringly long, perhaps over the lifespan of our own universe. Before we see any other reality like our own, it may be to the end of our own universe and its demise before another parallel universe like our world, the trajectory actually occurs again. But that might be the source of what we call maybe cosmological, eternity. That is, one gives way statistically, another one with the same history will keep up, and another, you and me, will live our lives just as we're doing now. So be rest assured that you've already lived 1,000 lives and died 1,000 deaths, and you have many and many more yet to come over an extremely long period of time. But when we're talking about infinity, right? When we're talking about eternity, it's not such a long time to wait. So with multiverse theory, you can bet I'll be back. Well, I hope you enjoyed this presentation today, and thanks for hanging in this far in. Thanks. Bye.